Thank you very much, Paul. You may be, most of you, a little young to recognize the truth of this, but when I was first asked to become head of the department and the concept of being a boss of a bunch of professors was posed to me, I was also told at the same time, it's not hard, it's like herding cats. So I'm not quite sure that I'm the boss of anybody, but I have a lot of cats to herd. I thought before I got started today, since this is a subject which has a lot of popular press, I would show you what chaos is like from a popular point of view. And so we'll start, hopefully, with something you should all recognize.
Dig a dinosaur? You have to get used to Dr. Mark. He suffers from a deplorable excess of You've never been suspiciously explaining yourself. Oh, no, because I hate this information. No. No, nonlinear equations? Strange attractors. Dr. Seneca, I refuse to believe that you aren't familiar with the concept of attraction.
Well, that's the popular view of chaos. And so we'll start right off with a question. What is deterministic chaos? Is it, in fact, Jeff Goldblum in shades and a black jacket, not a bad imitation of me, using strange attractor as a pickup line? How many people think that's what chaos is? All right. Well, one unconventional type up there. Well, I hate to disappoint the gentleman, but no, that is not it. Chaos is not that. Chaos, in fact, as we'll see in this talk, is an incredibly complicated and very unexpected, came as a surprise to almost everyone who worked in the field, dynamical behavior of certain nonlinear systems. And we'll describe all these words, if you don't know what they mean right now, that was discovered, well, was really appreciated beginning in the late 60s, was discovered in some sense in the early 60s, appreciated in the middle 70s, and of course you can look back to precursors that go back to the turn of the century, and I'll do a little bit of that. I wanted to stress, because ideally, if I had enough time, this talk would cover some other areas, that chaos is just one of several general properties of nonlinear systems, which are really quite unexpected. They're often called paradigms, and the existence of, I would say, probably 3 or 4 of these paradigms has led to the evolution of a whole new field called nonlinear science. In fact, I should define nonlinear science as sort of tautology. It's the study of those systems and the natural phenomena and the mathematical models which aren't linear. And as one of the famous, in fact, one of the founding fathers of this field, Stanislaw Ulam, Polish-American mathematician, noted, this is like calling the bulk of zoology the study of non-elephants, and therefore my title. The point is that almost all our ordinary systems, in fact, are nonlinear or have nonlinear regimes. But we historically have treated them in linear approximations because that's what we could solve. For instance, probably most of you know what happens when you stretch a rubber band. You may not be able to see much of this. Whoops, I've gone into the nonlinear regime already. When you stretch a rubber band at first, you get a linear force trying to restore it. How many of you have heard of Hooke's law? Hands up for Hooke's law. Okay, some small number. Anyway, the rubber band tries to pull itself back in a linear way. If you continue stretching it, it stays linear for a while, but then that's not linear. That's typical of nonlinear behavior. Or we could take a piece of your favorite spaghetti and bend it slightly in the linear regime, and pretty soon it goes nonlinear. Okay? So in most of the world is nonlinear. We don't see smooth, regular behavior. We see sharp changes in the nature of the system's behavior, and that's characteristic of a nonlinear system. If we're going to focus, though, today on the one particular paradigm, the paradigm of chaos, we need to start out by understanding, in some deep sense, what's special about nonlinear dynamical systems. So that's what I hope to teach you today. By the way, this is Stan Ulam and his wife, Françoise, pictured in the late 60s. Stan was a colleague at Los Alamos, and it was really quite remarkable to have discussions with him about this and other topics. Okay, we're going to start out by defining nonlinear dynamical systems. Well, nonlinear, I already told you, means things that aren't linear, and we'll come back to that in a minute. And dynamical system is simply anything that changes in time. So the thing that you study in high school physics most commonly is a pendulum oscillating back and forth in time. But a flower is a nonlinear dynamical system in this sense. A rock is a nonlinear dynamical system. It doesn't change very much, but it is a system. The one I want to introduce today, because it is, I think, essentially a guarantee that you won't forget these concepts, is the human heart. The human heart is a nonlinear dynamical system. I've written the word dissipative here. How many of you have some feeling for what I mean by dissipative? Okay, that's pretty good. What I mean by that is as a mechanical system, it doesn't conserve its mechanical energy. It loses energy to heat. And you sort of know that's true with in your heart, and that is true. It's a dissipative dynamical system. It's a dynamical system because it certainly changes in time. Normally, the heart has self-sustained oscillations. You do not need to plug your finger into the wall socket to get 60 hertz to make your heart beat. In fact, it's a bad idea to do that. Okay? And the rate, of course, is a function of stress. If you're late to class, or you know you haven't studied for the exam, or you're giving a lecture, your heartbeat goes way up. But when you discover you actually can do the problems on the exam, or that the teacher didn't see you sneaking into your seat, your rate goes back down to its normal, steady beat. So the normal behavior of the human heart is what a dynamical systems person, who knew a little bit more than Jeff Goldblum does in the movie, would call a limit cycle attractor. It's going around in a cycle, sort of periodic motion. An attractor, because if you perturb it, if you get the rate up, it comes back down. Now, there are other possible motions of the heart, other dynamical motions. There's one which is a very stable motion. That's no beating at all. In dynamical systems terms, that's called a fixed point attractor. And now I'd like you to do something that we're going to do several times during this talk. I want you to break the symmetry, form little groups of 3 or 4 people, turn to your neighbors, that's what TTN means, turn to your neighbors, and I want you to tell me what this fixed point attractor is called clinically. Just talk it over, introduce yourselves, talk it over, and give me an answer. Okay? Are there any brave groups ready to hazard the answer? Okay, down here. Okay, that's the fancy term is cardiac arrest. Who was thinking of the non-fancy term? What's a non-fancy term for it? Death, good. Okay. Full credit for either answer. Okay, so see what I mean? You wouldn't forget this? It turns out that many other motions are possible for the human heart. Maybe some of you remember when then President Bush had atrial fibrillations. Anybody remember that? Well, some of the teachers have to remember that. Anyway, that's one kind of arrhythmia. There's some fancy ones called the Wenckebach oscillations. Turns out the heart is a very complicated oscillator, has 2 parts. Normally they beat boom, 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 boom in sequence, but you can get beats where you have 4 of the first to only 3 of the second. That's called a Wenckebach oscillation. There are a huge number of these, and there's some behaviors which are so complex that they don't seem to show any clear periodicity. There's no obvious period. The heart is beating in an absolutely weird way. And there is some evidence, although it's not conclusive, that that kind of behavior is maybe described by a strange, not a fixed point or limit cycle, a strange attractor. And actually, this was sort of a mathematical joke that David Ruel and Florence Hawkins introduced into the literature in the 60s, and it stuck. So this is the sense of humor of the mathematicians. This thing was weird. They could have called it a weird attractor, but they stuck with strange. Actually, they named it in French, which is probably why it came through as strange. Anyway, strange attractor, as you know from Jurassic Park, is in fact a symptom of chaos. And the movie editors and the author did get that right. But we've gotten way ahead of ourselves. Let's go back and do what physicists always try to do, namely to get to the essence of the problem, what chaos really is and why it happens, and then try to make a very simple model that has chaos and allows us to see what's going on. Okay, this is a one-page summary of the essence of deterministic chaos. The definition, actually it's harder to define than it is to explain, is the seemingly random, erratic behavior in a system which is completely deterministic, that is, it obeys Newton's laws, for example, with no cheating. We don't put any so-called stochastic or random forces. There's no source of noise, there's no source of error. The erratic, complex behavior is intrinsic to the system. And this is actually very non-intuitive at first. You have the advantage of being young and not being biased by so many examples, but for my generation, the mechanics that we did in high school and college physics made this seem totally implausible. The reason actually that's non-intuitive to almost all of us is that we almost all carry inherently a clockwork view of the universe. This huge, giant tick, tick, tick clock. And for those of you who may know, have heard quantum mechanics, we'll leave this out entirely for this talk. I can answer a question about that later. To show you what I mean by a clockwork view of the universe, let me quote you some wonderful words by Laplace. Oops. Here's a picture of Pierre-Simon de Laplace, French philosopher and mathematician in the 1700s. And here's what Laplace said about the nature of the universe. An intellect which at any given moment knew all the forces that animate nature and the mutual positions of beings that comprise it, if this intellect were vast enough to submit its data to analysis, could condense into a single formula the movement of the greatest bodies of the universe and that of the lightest atom. For such an intellect, nothing would be uncertain, and the future, just like the past, would be present before its eyes. So complete determinism, knowing where things are, we know everything in the future. So here's a typical physicist universe. It has 5 particles, and I painted one of them green so we can watch it. And the rules of the game are, we know where every particle is at the initial time. We know all the forces, and they are completely well behaved. We know the particle's initial conditions, so we can solve F equals ma, and at the later time, any later time, we know exactly where every particle is. Some of them may have collided and interacted, but we know that. We know the interactions. We have complete predictability. In other words, from an exact knowledge of the initial state comes an exact knowledge of a final state. Now, this is true in Newtonian mechanics. As I said, I don't want to get into questions of quantum mechanics now, because the problem of chaos arises completely within classical physics and must be resolved by understanding what's going on in the classical world. The trick here is, and the hidden assumption, exact knowledge of the initial state is not achievable in a real-world experiment. Let's suppose you're trying to get an A in your physics course, and you're making some measurement, and to make it modern, let's make it a fancy measurement. You're looking at little particles that are suspended in a fluid, and you're watching them move around, and you're using laser Doppler interferometry. So you shine a laser on this particle, and when it moves, the velocity, you can watch the shift, the Doppler shift, and you can watch the motion. And the teacher says, look, if you can get a 10% measurement, you've got the A nailed. But then the teacher says, this is a great project, we've got to get you into the state science fair. And they want you to get not 10%, but 1%. And in the state science fair, you do well, but now there's a Westinghouse competition. Okay, we're getting serious. And they want you to get 1/100%. And you can see, the more accuracy I demand, eventually you're not going to be able to get it. The hidden assumption has always been that if you had roughly the same initial conditions, you'd end up with roughly the same final state. And it turns out that that is not true for certain nonlinear systems. They are exquisitely sensitive to initial conditions. The so-called sensitive dependence on initial conditions means that the tiniest error in the initial state leads to a huge error in the final state. And you cannot tell which final state you're going to get to from which initial state. Now, what's remarkable here is that Poincaré realized this. Actually, he realized it before. In about 1890, he wrote a famous essay on the three-body problem. But in 1908, he wrote a popular book in which he explained the essence of chaos. Now, there are many examples. How many of you have heard of the so-called butterfly effect? Yeah, this is again, a classic example taken from weather prediction. The idea that if the weather is so sensitive to initial conditions that if a butterfly flaps its wings in Beijing, the weather in the States changes a week later. Actually, speaking of weather, I forgot to put up my picture of Poincaré. Here's a picture of Poincaré, along with sort of a scientific pun. This is Poincaré in every frame, just scrambled. I thought, just to make sure we're talking about the same problem, I would make sure that we weren't talking about what you might call teen weather. This is idealized teen weather. So it's excellent here and it sucks there. But we're talking a little bit more precisely about the weather. And in particular, Poincaré again got it exactly right when he said, why have meteorologists such difficulty in predicting the weather with any certainty? Why is it that showers and even storms seem to come by chance, so that many people think it is quite natural to pray for rain or fine weather, though they would consider it ridiculous to ask for an eclipse by prayer? We see that great disturbances are generally produced in regions where the atmosphere is in unstable equilibrium. Remember that. The meteorologists see very well the equilibrium is unstable, that a cyclone will be formed somewhere, but exactly when, and they are not in a position to say. A tenth of a degree more or less at a given point, and the cyclone will burst out here and not there, and extend its ravages over districts it could otherwise have spared. So this is the sensitive dependence on initial conditions, which is the essence of deterministic chaos. Okay, let's consider a model for population. This was actually done, exactly this model. And we're going to consider the dynamics of a population, that is, the growth or decline in time of a population. What would the simplest model be? Well, it takes your parents to form you, and how many parents there are is sort of, if everyone has a child every year, that's sort of a measure of how many there can be. So the population next year is some constant, which is basically the birth rate, times the population this year. That's a pretty good starting model, good enough for government service. Let's make this mathematical. So we say Pn plus 1, n plus 1 is the subscript, n plus 1 means next year, is equal to Pn, the population this year, times r. This is a linear equation. Is everybody happy with that? Because P occurs only to the first power. And if I give you the population in year 0, then the population in year 1 is r times P0. In year 2, it's r times P1, which is in fact r squared times P0. In P3, it's r cubed times P0. Everybody happy? And the nth generation, it's r to the n times P0. And now let's have the second turn to your neighbor response. What happens to the population for very long times when this n, when this n goes to infinity? You turn to your neighbors and talk about that and give me the answer. Well, okay, that's enough time. Who wants to hazard a guess? Up here.
There's an infinite number of people.
Are there always an infinite number of people?
It's above 1.
Ah, okay.
If it wasn't above 1, then it would go to 0.
Okay, did everybody hear that? It depends on r, the birth rate. If r is bigger than 1, the population, if r is less than 1, the population dies out. If r is greater than 1, the population explodes to infinity. Only if r exactly is equal to 1 does it stay constant. In the real world, many factors, like the food supply or overcrowding, limit the population. And let's suppose there's a maximum population. Let's call it P max, okay? And that's, I just wrote P max there. And now I'm going to do something which physicists like to do. I'm going to make the problem simple by scaling everything. So I'm going to divide the actual population by the maximum value. And so the biggest, my new variable called xn, is 1, right? And now I'm going to write a simple nonlinear model which says as the population goes to the maximum, the population in the next generation tends to go to 0. So one way to do that is to put in a factor of 1 minus x. And here's my model. The population next year is r times the population this year times 1 minus the population this year, how near we are to the maximum. This is something called the logistic map. It's a nonlinear, by the way, this is called a map by dynamical systems people because it maps the population this year onto the next one. I had that written earlier, but I didn't mention it. It's nonlinear because here's xn times xn, xn squared. That's not linear. Okay. Question. You know what a fixed point attractor is. And for the heart, it was death, no beating. Does this model have a fixed point attractor? Come on, I don't hear much talking. Okay, any group want to hazard a guess? Any group? Who said yes? Not just yes or no, why? Well, what's the answer? Who said yes over here? That is correct. It does have a fixed point attractor. What else can you say about it? That's interesting. Does anybody know what is the value of x star? Okay, well, let's just think about this for a minute. xn plus 1 and xn have to be the same number, right? X star. And so this xn also has to be the same number. So let's just solve it. That's just a little bit of algebra. So here's the answer. And I'll leave it up long enough for you to copy it. Okay? All right. Let's, well, we know the limits of what we can push. Let's see how many of you have programmable calculators either right now or in your pockets, in your backpacks, or nearby. Those of you who are really good at programmable calculators, I'll race you to the bottom of this transparency. Okay? You plug in the equation I said, an iterative equation. For r between 1 and 3, the model has a fixed point attractor, but it's at x star equals 1 minus 1 over r, that other fixed point. So we have a stable population which is not 0. What happens to the fixed point, this x equals 0 fixed point, for r bigger than 1? Turn to your neighbors and see what you can come up with. First, let's ask the question, does it go away? Anybody? Do you think it goes away? Okay, the answer is it doesn't go away. It can't go away. X equals 0 is still a solution to the fixed point equation. What else can happen to it? Okay, well, they didn't use this line in the movie because it was pretty clear that the actress was not a repeller, but it turns out that the fixed point becomes unstable. And instead of being an attractor, it becomes a repeller. And so it repels solutions away from it. Instead of being attracted to it, they repel. So this is something that will come up, is very important for our later discussion. Whenever we get a change in this system and these solutions seem to disappear, they don't actually disappear. They're still there. They're just unstable. And that's extremely important. Okay. What happens? Question. Yeah, by the way, Paul's comment that we want to have questions, please, if there's any confusion, this should be absolutely lucid. You should be able to reproduce it all. And hopefully you'll be able to for the quiz, because there will be one. Otherwise, you won't get to go to the football game. Only people who pass. Okay, what happens for r bigger than 3? Well, let me show you with a series of things. Instead of having one value, notice as you start from the left here, you can't see, you can't see, but this number is 3.4, and it goes from 3.4 to 4. Notice that there are 2 values of x on the vertical axis, okay? And then suddenly you get 4 values, and then you get 8 values. What you get is a sequence of limit cycle attractors. First period 2, then period 4, then period 8, then period 16, all the way up to all powers of 2, all before a finite value of this r. Let me show you another thing, then we'll go to the computer demo, which probably makes this clearer. I should have skipped these slides, I think. You can probably just barely see in this picture of this attracting set a little tiny box. Look at 3.7. You see that in the middle at R? Go over 1 unit, half a unit, and up. In the bottom line there, you see at the bottom part of that graph, you see a little box. How many see it? Come on, you've got young eyes. You've got to be able to see that. I can see it. Okay. Unfortunately, I can't point to it. You'll see it in a minute, a bigger thing. I'm now going to blow up that region. The reason I have these slides is because the computer isn't able to blow up now. And you get, what does it look like? Same thing, flipped over. What do you think would happen if I went up to this top region up there and put a little box around it and blew it up? Same thing. So remember, this is a simple equation, x times 1 minus x, iterated, and this is the dynamical behavior that it produces in time. Incredibly complicated behavior which has the same structure on all scales, called a fractal. Let me go ahead and try to switch over to the computer. Now I'm iterating the logistic map, and here's what you see. What this does is it iterates for 200 times, it throws out the first 100, and then plots the next 100 points. What happens between r equals 0 and 1? Anybody? What does the population go to? What happens between 1 and 3? At every value of r, it goes to a fixed point. And does this look like the curve 1 minus 1 over r? It better. Okay? So my analysis is right. And bingo, suddenly at 3, we get a bifurcation, that is like breaking the spaghetti, a change in the nature of the solution, where you get a period 2 solution. And question? The value 3 is nothing's important about it. Just that's the point at which it happens. The question was, what is important about the value r equals 3? And the answer is nothing. It's an accident that this bifurcation happens there. But once it happens there, it turns out that the other r's are pretty much determined. And here you can hardly see, this is why I didn't use this entirely, because you can't see. Normally I should be able to drag across here and blow this up, but I can't. It's not, that functionality is not working on this machine. And so here you see 1, 2, 3, 4, right? What you can't see are the 8, 16, 32, which you could see on the other plot. But what you remember what this is. This is how the population changes from year to year as a function of basically the birth rate. So at this point, the population in even years is one value, in odd years it's the next, and it goes back and bounces back and forth. Here the population has a 4-year cycle, 1, 2, 3, 4. And what actually happens in this simple model is that you get an infinite number of these transitions, all before r equals 3.59, which is about here, and you get the so-called period doubling transition to chaos. I don't have a lot of time to go into the details here, but you can see that this is an incredibly complicated behavior from a very simple system. This period doubling transition was studied actually also at Los Alamos, it turns out, by Mitchell Feigenbaum, shown here, and of course with the appropriate disclaimer that the Department of Physics does not encourage the smoking of cigarettes. Mitchell, however, does smoke cigarettes. He may well be the character who inspired Ian Malcolm. He was at Los Alamos at the time, and he worked out this whole period doubling transition to chaos. You wouldn't think it would be exciting because it, after all, is a simple quadratic equation which you can teach, if you have enough time, to a 12-year-old. But in fact, Mitchell pointed out this transition was universal. Namely, you can observe it in the real world, not just in the simple mathematical model. Many, many nonlinear systems. The pendulum, if you drive it and damp it. Electrical circuits, which we'll do here in a minute. And fluid flows, as studied by Albert Liebschaber, all show this period doubling transition to chaos. Let me just show you some data. This is not, I didn't put this in the slides because it's a little bit more detailed than you want to know. This is sort of a proof of principle. Here is the experimental data showing that you had one period, you found period doubling means frequency halving, right? You found half the frequency, then you found a quarter of the frequency, then you found an eighth, plus, and so on. And this obeyed the predictions of Feigenbaum, not just qualitatively, but quantitatively. How do we know when we have regular behavior, periodic behavior, as over here, sorry, and when we have chaos. Well, it turns out that something else which is shown in this slide is a measure of that. It's something called the Lyapunov exponent, and that is a very simple concept. If things are going to separate in time, they're separating, if they're sensitively dependent to initial conditions, what we actually mean by that mathematically is that they separate exponentially in time. And they do so if this so-called Lyapunov exponent is positive, and down here in this computer demo you see the Lyapunov exponent for the logistic map plotted as a function of r. And what you notice is that in this region over here, there are many places where lambda is positive. In those regions, the system is chaotic. Wherever lambda is positive, the system has chaotic behavior, and the actual nature of the attractor is not a fixed point, it's not a limit cycle, but it is one of these strange attractors. So a strange attractor exists in this very simple system. I also have another demo, which we can play with afterwards, which is sufficiently annoying. I won't do it very much. It's an oscillating electrical circuit which shows this transition to chaos. I've actually gone past it already. What you can see, you hear one tone, and now you start hearing growling. Hear the growling? Those are the lower frequencies. Period doubling means frequency halving. We've gone through several of these frequency halves already. I won't do much of this because A, it's annoying, and B, we're running a little bit late. But the whole point of to remember is the Lyapunov exponent measures the sensitive dependence on initial conditions. Okay, the next page is just some homework for you. I just put it up to tell you what it is. You can solve yourself analytically for the period 2 orbit if you want. Not hard. Just an algebraic equation. Okay, that's great. But what about this strange attractor? I talked about it, but I haven't done much with it. What is a strange attractor, and what does it look like? Okay, now we have another one of our turn to our neighbor sort of discussions. Can this strange attractor consist of a finite number of points? Talk to each other. Convince each other one way or the other. What do you think? Okay, enough time. Is anybody ready to hazard a guess? Any group? Any group? Yes, no, maybe? Can it be a finite number of points? Oh, come on, you guys. Oh, no, but it isn't truly random. Just within this model, can the comment was if it's truly random, no, which is true, but it's not relevant here. From this system, could this attractor be a finite number of points? Well, finite means that whatever it is, I can name it, okay? So finite is any number, whatever it is, it's finite. So let's say 27, doesn't matter. If it's a finite number of points, then after a finite number of steps, you have to come back to one of the points you've already been at, right? Everybody sees that? If you have n points, let's say 4, after 4 steps, you have to come back to one of the ones you've been there before, right? Everybody agree? Is that clear? And once you come back to the one where you've been before, the model is deterministic. It takes you to the next point. So if it's a finite number of points, you have to have a periodic orbit. So the strange attractor cannot be a finite number of points. It's something really weird. Okay? If it were finite, it would have to be periodic because the map is deterministic. In fact, it turns out that exactly at this value r infinity, 3.59, etc., there is a strange attractor which is much, much bigger than any collection of points, but much, much smaller than any line segment. A point has dimension 0 geometrically. A line has dimension 1 geometrically, just like a square has dimension 2 and a cube 3. It turns out these strange attractors have dimension, in particular, this particular one has dimension 0.538, a fractional dimension. This is the subject of fractals, which I wish I was actually planning to go into. I'm very glad I didn't because I'm already quite late and wouldn't have gotten through it at all. But I can answer questions about that later. These strange attractors are weird babies. They have fractional dimensions. We're going to get some geometrical insight into the strange attractor. I'm going to give a description here in words, and then I'm going to ask for someone who feels really confident about his or her ability to roll out dough to come up and demonstrate, not dough in the sense of cash, dough in the sense of stuff that you bake with, and we'll show you how strange attractors work. Okay. Turns out that the logistic map is too hard for me to do this demonstration, so I'm going to do what physicists do when they run into a problem that's too hard. They make it simpler. Instead of the logistic map, which is shown here as this simple parabola, this is the curve xn times 1 minus xn, I do what's called a tent map, which is a straight line approximation. Obvious reason for calling it tent map. If I then look at what the tent map does, I'll go through this quickly. After the first iteration, I'm looking at the tent map when a equals 2, so the map takes x into twice x when x is between 0 and a half, and it takes x into twice times 1 minus x, which is this line, when x is bigger than a half. So what happens? 0 to a quarter is mapped to 0 to a half, right? Twice x. A quarter to a half is mapped to half to 1. But a half to 3/4 is mapped from 1 back to a half. And 3/4 to 1 is mapped from a half back to 0. This stretches the interval. But it maps it back so it also folds it. So the whole secret of how you can have something weird like a strange attractor is you get a stretching, and the stretching is directly related to this Lyapunov exponent, the fact things are separating exponentially, but the nonlinearity folds it back over. And so it keeps it in this interval. And so you can see that after one iteration, you have this thing folded over twice. After 2, it's folded over 4 times, etc. This is very much like making puff pastry, where you roll out the pastry, you put it in the butter, you fold it over, you roll it out, you put it on. And when you bake puff pastry, what do you get? What do you buy in a store? Typically. I mean, what do the French eat for breakfast? Croissant. Okay. Now, which is heavier for a given size, a croissant or a bagel? Why? Because the bagel is solid. A bagel has dimension 3. It's a real object. A croissant is flaky. It's light. It's actually like a fractal. It has a dimension slightly less than 3. And that may sound stupid, but it's actually it's close to the truth. So what I'd like now is for somebody to come down here and show us how this Baker's transformation works in real life. Anybody? Anybody? Okay, Gwen, come on down. While she's doing that, I'm going to go on and take... So what we're going to do here is put a little bit of blue-colored dough. This is what you want to do is just try to roll it out. Make sure you roll it evenly. So the white and the blue... Actually, let's do it. I want to cheat to make it a little faster. Roll it out this way, and then fold it over, put the blue on the outside, and roll it again. Okay, just... Okay, now fold it over on the outside. Okay, well, okay, now roll it out again. Again, about a factor of 2. And the white too. Don't just do the blue. Don't cheat. Uniform stretching. Okay. Now fold it over again. And look, what's happened? What's happened? Okay, this blue is spread out through the whole attractor. Okay? It started out in a tiny little region, and after only a few iterations, it spread over the whole attractor. And that's exactly what the secret of the sensitive dependence on initial condition is. Thanks, Gwen. That's okay. Let's now go to a picture gallery of chaos. I'm going to try to do a bunch of slides to show you how these things, how this works in a variety of different systems. Why is this not working? Oh, okay. This was a picture of the Lyapunov exponent. It's a different calculation. We've already talked about it. This is a picture of something called the Lorentz attractor. As the transparency says, this was a model. The equations that describe this system were written down by Edward Lorentz, who was actually the man who invented the concept of butterfly effect. I won't write the equations for you, but what you see is this sort of, what this looks like is sort of a many layered slinky. It looks like your kid brother's slinky, except you bent it and you stepped on it, okay? And so it has 2 lobes instead of 1. And it winds around, all those little orbits wind around. They're actually colored blue and green. It's hard to see in this depiction, especially because they look white when they overlap. but the orbits wind around in that space. It never touches itself, otherwise it would be a periodic orbit, and it goes on forever, winding around, okay, in a finite region. So it's like doing this folding and stretching forever. Here's another view of it. That's of two lobes of the Lorentz attractor. Actually, if I drive this system chaotic, well, you have to look down here. Eventually, that's also a two-lobe attractor. If I were good at the oscilloscope, I'd be able to get the vertical to spread it out, but I can't right now. This thing, if you look at it from the side, it looks a little bit like a sheet, but it's thick. It's this puff pastry that we talked about, okay? It has a thickness in the third direction, and in fact, the Lorentz attractor is here's another view up close. What this shows is that the green, which you can now see here, and the blue are interwoven on all scales. Just like when you look at this thing from the side, the blue and the white are interwoven on all scales from when Gwen rolled it over. Okay? So the actual dimension of the Lorentz attractor is 2.05. It's bigger than a surface, but smaller than a solid. And the image you want to keep in your mind is the difference between a bagel and a croissant. Okay. Okay, what about the sensitive dependence on initial conditions? Here's another example. This is incredible. This is what happens to a pendulum, like you do in a high school project, when you put some driving and damping on it. What you see is a big red region and a big blue region, right? And in between you see sort of, well, there's some green and some yellow and some black, but you also see a lot of red and blue in between. The blue region is when the pendulum ends up, well, what this is a plot of where you start the pendulum with a certain angle and a certain velocity. And this tells you how the final motion of the pendulum is. So where it's blue, where you started the pendulum and it swings around for you counterclockwise. Where it's red, you start the pendulum and it swings around for you clockwise. Now those motions are simple, they're periodic, okay? Some of the other motions, like the yellow and the black, are more complicated, and in fact are these attractors I've been talking about. But I want to talk about a different aspect of sensitive dependence. Notice that there's a region, right sort of through the middle, where it's clear if you move the points a little bit, you're going to stay in the blue region. Everybody see that? It's a big solid blue region. There's a big solid red region. In between, however, and you can see it better on the actual slide, there are red, blue, alternating on every scale, the finest possible scale. So if you make the tiniest error in the initial way you start the pendulum, it'll end up going this way instead of that way. And that's the basis of a lot of these toys that you see, these so-called chaotic toys that float around. Okay, I've stressed also the idea of dissipative systems, chaos and dissipative systems. It turns out that chaos can also exist in energy-conserving systems, and the best example in the real world that we know is the solar system. The solar system has, although it has some dissipation in it, it's very, very much like the music of the spheres. I mean, a perfect mechanical system. In conservative systems, chaos still exists, but there are no attractors. And what you see instead of these attractors, this is an example of a conservative chaotic system. Yeah, the focus is just not sharp here. What you're supposed to notice here is the round things are periodic orbits. The sort of stuff in the middle here, but around Q equals 0.5, where you see a dust, is the chaotic area, the so-called Cantor dust. Can you see the small little square inside the big square? Everybody sees that? This is what's inside the small little square. Can you see the small little square? That's what's inside that small little square. You see the small little square? Again, you get the point? You see the small little square? Okay. Now this has a good story. This is a lesson for students. This was done at the CNLS that Paul mentioned before, the Center for Nonlinear Studies, over a weekend by 2 of our graduate students. It took a long time to do this calculation, because look how tiny that square is in terms of the values of P and Q. It's about a 10,000th across. So you have to wait a long time for the map to come back to that point, right? You see those little Halloween-like eyes. They stopped there because they found the monster in the machine. Actually, they didn't stop there because of the monster. They stopped there because they ran out of money, because they spent the entire budget of the CNLS computing for the quarter doing this computation. So, you've got to be careful about cutting off your calculations. We managed to get it back, but that was an expensive pastime. Okay. I want to close with some examples that chaos is practical. And I think I've already convinced you that systems in the nonlinear regime can show much more interesting behavior than they can in the linear regime. We saw the population could go to a stable, sustainable value in a nonlinear model, whereas it couldn't in a linear one. An example, which is another demonstration, which I need a volunteer for to come up and do. Okay, come on, Alex. Okay, this demo is tricky, and given that the other one didn't even work all that well, this one may be a disaster. Okay, Alex, what you have to do, this is a chemistry demo, okay? All right. You have to take equal amounts of these three solutions, pour them in here, and see what happens. So if you take 15 milliliters of the other two and pour them in there while I'm talking, okay? So this is if this works, what you're going to see is a chemical reaction that oscillates, that changes color. Okay, so it's a nonlinear oscillator. Why is this interesting? Well, one reason it's interesting, and this is a good lesson for you too, is that it was declared to be impossible by experts in the field as recently as 15 or 20 years ago. You couldn't have chemical oscillations. Well, by then they'd know you could have oscillations. You couldn't have chemical chaos. And they were wrong. How could this be? These people are smart. Okay? It could be because they assumed that when you started your chemical reaction, you were very near equilibrium. They assumed you were linearly close to equilibrium. And they made a linear approximation around equilibrium. As soon as they relaxed that and went to nonlinear distances from equilibrium, bingo, you saw this behavior. Okay. Now, whether this is going to work or not, we'll see. If that doesn't work, Alex, I'm going to give you another set of solutions. What this should do is oscillate between yellow and blue. And if it doesn't do it in a couple minutes, we'll go to the other set of solutions. It turns out that chaos is a much more complicated motion, as we've said, and it implies much more flexibility. In the chaotic system, you have essentially, if you recall in the logistic map, I told you to think about what happened to the fixed points when they became unstable, when they disappeared, when you didn't see them in the attractors. What happened to them? Come on. They became unstable. They became unstable, right? But they were still there. It turns out the same thing happens to the period 2 orbits. And the period, go ahead, Alex, you better sit down on it. It's not seeming to work. And I'll try the other thing later. The period 2 and period 4 and period 8 orbits, they're all there. They're just unstable. And so generally, in a chaotic system, you have a huge number of unstable periodic orbits. Now, that means that if you can figure out how to stabilize a periodic orbit, you're going to end up with the ability to control a system to do whatever you want. So chaos is very flexible. And let me show you what it's like to stabilize. Well, let's don't do a periodic orbit. Let's do a fixed point. A fixed point is a simple case of a periodic orbit. Is it turning blue? No. Okay, okay, good. It's finally oscillating. Oh, it's just you had to be patient. Okay. Now we'll see whether it comes back. Yeah, this is very. It may not oscillate. A watched oscillator never oscillates. Watch this. This is chaotic control. Period 2 of a map is a fixed point of the second iterate of the map. We discussed that in an earlier slide, right? If you iterate the map twice, you come back to the same value. So if I can show you how to stabilize an unstable fixed point, I've shown you how to stabilize a periodic orbit. You just have to take the iterate of the map, which corresponds to the period that you want to stabilize. Here's how you stabilize an unstable, and you know it's unstable because Marian's worried. Is it oscillating? Great. Okay, so it worked. Okay, now you can watch this. This should go. It will go back and forth between blue and clear with a yellow stage in between. It is a chemical oscillator. This one was pretty close to dead, but it just barely made it. Anyway, does everybody see that this stabilizes? I can stabilize by moving my hand this unstable fixed point. And that's basically the idea behind chaotic control. You can lock into any of the very many possible motions. Those who are interested come up here afterwards, and we'll try to see if we can get the other reaction to go and be a little more spectacular. Okay, well, one of the things that's important to realize is that, chaos itself is very interesting and useful. This is off the cover of Science. This is something you're trying to mix. If you want to mix two things together, just like mixing the blue dough with the white dough, you obviously want to mix it as fast as possible. Well, chaotic motion is perfect for that. So sometimes you want to have chaos, as I said here. Alternatively, suppose you're Mercedes or BMW and you're building a transmission and you have some losses. It loses and it sort of knocks around inside. Would you rather have the losses come at a fixed period, so your transmission goes clank, 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 or would you rather have it go with a lot of different frequencies in it? I mean, it's pretty obvious. It will only go clank for so long before it falls apart. So you want to have the kind of chaos which allows you to have a broad range of frequencies in the response of the system. Finally, I can see Paul sitting on the edge of his seat, not because of his interest, but because I'm running way over time. I want to run through some pictures of chaotic control. This is the latest stuff that's been done on how you use chaotic control for important processes. This one is a picture from basically the first article in the physics literature on chaotic control. It was actually an article written by our colleague here at Illinois, Alfred Hubler. He was then in Germany, which is why he wrote it in German. What you're supposed to notice is that you had this very irregular behavior on the left, and then suddenly he was able to lock the motion into a periodic motion and control the amplitude. One of the most important advances was associated with this experiment, which is a magnetoelastic ribbon, a ribbon whose Young's modulus, its strength basically, strength against buckling, is strongly influenced by a magnetic field. And if you take off the field, it becomes weak. If you put on the field, it gets rigid. And you can make this thing go chaotic. On the left of the graph, you see what amounts to basically the strange attractor in a logistic map sense. On the right, you see what amounts to a fixed point. And they turned on the chaotic control, bingo, they nailed it. This was work by Bill Ditto. His name will come up later. This is work in a closed fluid system. The fluid was flowing this way and back. It's sort of like the pendulum description I had. Again, it was random, and suddenly you turn on this chaotic control and you can lock it in. Finally, some slides. This is work done at Georgia Tech by Raj Roy. What you see here is that the laser, what you want to notice is the chaotic regions are the stars, and the steady state is the solid line, the solid blob. You want a steady state out of this laser. That's the mode they want to operate in. It shows this chaotic and periodic response. Using chaotic control techniques, you can stabilize it over the whole range. It's a very important stabilization for lasers. Okay, finally, let me summarize. And what you see here are a whole bunch of underlying words which I hope you would be able, if we actually did have a quiz, to give me some understanding of. We've talked about all of these concepts, and they now should mean something to you. You should know now that deterministic chaos is this seemingly random, erratic behavior in nonlinear dynamical systems, like the heart, which arises because the system stretches and folds. It's incredibly sensitive to initial conditions. The exponential separation of the nearby states leads to the stretching. The nonlinearity leads to the folding. The stretching is quantified by the Lyapunov exponent. Together, the stretching and folding produce a croissant-like, a flaky fractal structure for these strange attractors that describe chaos. Chaos also exists, although no attractors do, in energy-conserving systems like the solar system. Applications of chaos and interest in chaos, chaos can be understood with very simple models. If you have your little calculator, go home and play with it, you'll see exactly everything you saw on the big fancy computer on your little computer. Chaos provides an explanation of many important natural phenomena because of the universality of things like the period doubling transition to chaos. You can see it in electric circuits, in fluid flows, and so forth. And finally, chaos can be used to develop novel ways of controlling complex behavior, of making a nonlinear system do what you want. It gives great flexibility, and it may save your life one day. Thank you very much.